Good morning, everyone. This is Mr. Couple. Today is my physics lesson. This is Tuesday morning. We're going to be learning today about Ohm's law and some other ideas like electrical shocks and alternating and direct current, as well as electron drift velocity. I have one student with me this morning. It's Mayar. Say hello, Mayar.
Good morrow.
I have told Mayar that if she has any questions at all, that she should ask them, and that's the whole benefit of being here for the live recording. I strongly encourage you guys to come. We do it on Tuesday mornings at 11 o'clock and Thursday afternoons at 1 p.m. Let's begin. So we're going to first talk about this guy. His name is George Ohm. I mentioned him briefly in the last lesson, but what George Ohm discovered was this relationship called Ohm's law, and Ohm's law is written out over there: current equals voltage divided by resistance. These are all the electrical concepts that we've been learning about so far, where current is the rate that charge flows through a circuit. You could have a high current by either having fast charges, like zoom, 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 like zipping past, or by having a lot of charges going by slowly. Voltage is that idea of the potential difference. It's sort of the amount of energy that you can give to a coulomb of charge. And then resistance is how much the material obstructs the charges from flowing through it. And so George Ohm discovered this relationship between those three quantities, and it's called Ohm's law. What's interesting is that it's not actually a law, that it doesn't actually work in all cases. It's a simplified version. The real truth of it is something we talk about in IB physics. So I hope you guys join me in IB physics. All right, let's give the units. So if we look at this equation, current equals voltage over resistance. If we write out the units, so the units of current are amperes. Most people just call those amps. So that means that an ampere or an amp is going to be equal to a volt. We'll try to write that more clearly. A volt divided by an ohm. The symbol for the ampere is an A. The symbol for the volt is a capital V. And the symbol for an ohm is the omega. All of these units are named after scientists, which is why their letters are capitalized. So Ampere was a person who discovered that current carrying wires can actually exert forces on each other. Uh, Volt is named after this guy named Volta, who invented the electric cell. And an ohm is named after George Ohm, who discovered this relationship between these quantities. There are three common mathematical forms that you'll see for Ohm's law. And so you'll see them written out with the symbols of these quantities. So I is the symbol for current equals V over R. So that's the form that we see up there defined in this equation, which is the default form that you'll typically see it. That's sort of how Ohm said, he said like current is calculated through this. You could also rearrange these variables to solve for the voltage, where you'd multiply both sides by R and you get V equals IR, or I like to call that version VER. Or you can solve this for R, which would mean just swapping the R and the I, swapping places with those two. And then you get the last version of Ohm's law, which is R equals V over I. I'm going to erase that. And that's just the little algebraic manipulations. But those are all the same equation. They're just Ohm's law. So let's write down a general statement of Ohm's law. And Mayar, if you have any questions, just jump in at any time. Just like tell me to stop and I'll stop. If we want to write out a general statement of Ohm's law, what we can say is this. So if we have, if 1 volt is impressed across a conductor with resistance 1 ohm, what was that? If 1 volt is impressed across a conductor with the resistance of 1 ohm, I cannot draw an ohm at this angle. Let's try that one more time. Okay, close enough. If 1 volt is impressed across a conductor with a resistance 1 ohm, then 1 amp of current is established. That's the generic statement of Ohm's law. So it's basically saying, hey, look, if you know how much potential difference there is, and you know the resistance of the conductor that you're establishing that difference across, well, remember, a potential difference is what causes charges to flow. And so if you know how much potential difference there is, and you know what the resistance of that material is, then boom, you could figure out how much current is going to flow through that conductor. There's two mathematical relationships here. We can pull them out of this expression. So there's a direct relationship between the current And the voltage, I'm having trouble erasing this, it's not working. There's a direct relationship between the current and the voltage, and then there's an inverse relationship between the current and the resistance. So simply put, if you have a higher potential difference, you're going to have a higher current that flows. And in the opposite, if you have a higher resistance, you're going to have a lower current that flows. So for example, if you double the potential difference, it'll double the current. But if you double the resistance, it will have the current. Just typical relationships like we're used to. The first question on the boring worksheet is going to be asking you about this. So that's why I'm mentioning it to you. So basically, what Ohm's law says is if you want to figure out the current that's going to flow through a conductor, then you need to know the resistance. So I thought it'd be helpful to show you guys some common resistances that various objects that you might be familiar with have. So the resistance of a cable, like a copper conducting cable, is less than an ohm. So it's a very, very low resistance. And the reason is because you don't want those things to be dissipating the energy. You want the electricity to flow through it unimpeded. And so wires have a very low resistance. Light bulbs, this is an incandescent light bulb. They have very high resistances, 100 ohms. And so that's what allows it to heat up and light up. So that resistance is going to, sort of dissipate the energy. That's what resistors do is they dissipate energy. So the electrons as they're traveling through the wire, they like bong 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 bong, like they bong 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 like pinball, they like bonk into the atoms in the wire and then they give off energy. So that's what's happening inside a light bulb. And a toaster is typically around 15 to 20 ohms, so I just went with the 20 ohms on that. So if you've ever looked inside a toaster, you can see those little like heating coils in there. Those have a resistance of about 20 ohms. All right, so why is this relevant? Well, if you look at the outlet, electrical outlet in your house, there are three wires that connect to your electrical outlet. So we call one of them is the hot wire or the live wire. So this is where you have the actual potential that's being established. Then you have a neutral wire, which has no potential on it. It's just neutral. And then you have the ground wire. So we'll be talking more about the ground wire a little bit later. But the basic idea is that across these two terminals, so if you plug in, this device is called a multimeter. So if we plug in a multimeter to these two terminals, we can measure what the voltage is across those two terminals. And so we can see right here that in the United States of America, we use 120 volts as our potential difference inside an electrical outlet. So if we come back up here and we think, all right, let's have these devices plugged into the wall. So that means that we're going to have, if we have the voltage divided by the ohms or the volt divided by the resistance, the voltage divided by the resistance, we know that the voltage is 120 volts. So if all of these guys are operating at 120 volts, we can calculate what the current in these devices would be by simply dividing them. So this is our voltage. And so now we can calculate the current by using Ohm's law. So to find the current, we just take the voltage divided by the resistance. So the current in this case is 120 divided by 1, which would be 120 amps, which is a very large current. That would, if you just ran 120 amps through a wire, like if you just took two ends of a wire and just plugged it into the wall, there'd be no resistance on that wire, and that wire would basically melt. Like it'd get so hot, there'd be so much current flowing through it that the wire would just melt. This is why you shouldn't put a paper clip into an electrical outlet because it will it'll fry it. They usually call that a short circuit. Okay, next, 120 divided by 100, so that's 1.2 amps. And then in a toaster, 120 divided by 20, so 12 divided by 2 is 6, so that's 6 amps because the zeros are going to cancel out. So that's what you're looking at in typical electronic devices. You'd usually have like in a vacuum cleaner or a toaster, you're going to have on the order of some number of amps. So that's like household is typical, like a household circuit would have like a 15 amp circuit on it. So that's generally what you're looking at there. Okay, so why is Ohm's law important? So the reason Ohm's law is important is because it determines what the current will be. So if you know what the potential difference is and you know what the resistance is, you can determine the current. And so generally when you're operating an electronic device, you're going to want the device to have a certain amount of current flowing through it. And so Ohm's law allows you to determine what that current's going to be. And it's based on the potential difference or like your battery or your voltage supply. Whether you're plugging into the wall or using a battery or something like that, that's going to set what your voltage is. And then depending upon what current you want, you're going to need a certain amount of resistance in your circuit. So these devices here, these devices are called resistors. And resistors are used inside electronic devices to regulate the current. So that way you don't get too much current or you don't get too little current. You want the resistance in that circuit to be just right, so you get just the right amount of current flowing through it. So these generally on circuit diagrams, you'll see these things written like this. Like they'll be kind of like these squiggly things, which are supposed to show like the current reaches this thing and it kind of like gets obstructed, like it gets blocked by it. That's what resistors do. And if you've ever taken apart a computer or looked at like a circuit board, like a motherboard or a graphics card inside a computer, there's also resistors in there too. And those are these little box looking things there. Those are resistors printed onto a circuit board. There's other devices there as well. So this is some sort of an integrated circuit, like a chip that's made of transistors. And then these things out here, those are capacitors. We'll talk about capacitors a little bit later. You might remember from a previous lesson, we said that capacitors store charge. So their job is to basically absorb charge from a circuit and build it up in like a reservoir of charge, like they store up all that charge. Generally, in a device like this, you have all these resistors, like in a TV or a computer or a phone. You'll have a bunch of resistors in there, and they could be anywhere from a few ohms to like millions of ohms, even some that are like milliohms. So depending upon what sort of currents you want to flow through your device and through different parts of your device, you just need to change the resistance. And so that's essentially Ohm's law. Ohm's law is one of the most useful tools for electricians. They use it all the time. All right, I just took this picture a couple minutes ago. So what I'm doing is I'm holding a battery between my two fingers. There's a potential difference across my two fingers of 1.5 volts. That's the potential difference of a AA battery like this, or just any alkaline batteries to be about 1.5 volts. So my question is, why doesn't a current flow through my fingers? Do you know, Mayor?
Um, I'd appreciate it if you'd stop picking on me, but
Oh, wow, okay.
no, but it's because is it because there isn't a resistance?
So there is a resistance, but that's a good
Uh,
idea, right? So you're going to need two things. So we have a voltage, right? 1.5 volts. But what's the resistance? Well, the resistance is actually the resistance of my hand. So my hand is going to act. I should do a different color. My fingers are going to act like the resistor in this circuit. So it turns out the resistance of a human hand or fingers like this is about 100,000 ohms. So what happens is we've got a pretty small voltage, 1.5 volts, and a huge resistance. So if you have a small voltage, that's going to cause there to be a small current. And if you have a huge resistance, that's going to cause there to be small current. And so both of these things are contributing there to being no current. Well, or the current is so small, it's not able to pass through. Like there's just too much resistance in my hand, so the current can't flow through my fingers. So I'm not going to get shocked from a 1.5 volt battery. The resistance of my hands are just too large. So this gives a question: is it possible to send current through a human? So could we actually like electrocute humans? Well, realize that if you want an appreciable current to flow through a human, the resistance is fixed. It's going to be 100,000 ohms. So that would mean that you would need to do two things: either lower that resistance somehow, or establish a very, 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 or impress a very, very high voltage across a human. So humans can be electrocuted. You either need extremely high voltages, or you need to lower the resistance.
guess I have my plans for the weekend.
You're going to electrocute yourself? Please don't. The way that you lower your resistance is you just get wet. If you get wet, what will happen is the salts from your sweat and when you perspire, the salts will dissolve into the water, and then salts are really good conductors. And so what will happen is that now you have like this layer of salt water surrounding you, and so now current can actually flow through you. So if I grab this battery while my hands were wet, it's possible that my resistance would be lowered to where I can feel like a tingling sensation. And then if you increase that voltage even higher and higher and higher, it could be enough to actually shock you. So I grabbed this out of the textbook. Basically, I'm just going to summarize what it says. Well, like you can imagine, like if your hands are dry, like you're not going to get electrocuted. Like it's very unlikely that that'll happen. You need an extremely high voltage, and there just really aren't any in everyday life. There aren't any voltage sources that are that high. However, if you're in a bathtub and you're bare feet with water and you're wet, then the bathtub is actually connected through the electrical plumbing to the ground of your house. To like, and so what can happen is if you get exposed to a high potential, like a vacuum cleaner or no, that's a vacuum cleaner, hair dryer, and you touch the hair dryer and the hair dryer is at 120 volts, and then your feet in the bathtub are connected to ground, which is neutral, there'll be a potential difference. And since you're wet, current can actually flow through you, and it can electrocute you and kill you. Like lots of people every year die from this. Like you hear stories in the news all the time of people getting electrocuted in their bathtub. So using electrical devices when you're in the bath is a big no-no. And the reason is because your resistance is significantly lowered when you're wet. So don't use electrical devices when you're wet. Doesn't mean it's going to kill you. It just don't do it. It's not a good idea. So the idea here is if you want to get shocked, right, if current is going to flow through you, then there needs to be a potential difference across your body. And so one thing is interesting is like if you've ever seen birds on these high voltage power lines, why don't the birds get shocked? I mean, like the bird is touching this extremely high voltage power line, like hundreds of thousands of volts. Why isn't the bird getting burnt to a crisp? And the reason is because both sides of the bird are touching the same wire. And if that wire is at, some, let's say, positive 100,000 volts, then what's the difference between the two sides of the bird's feet? The potential difference is zero. So the bird doesn't get shocked because the voltage is equal to zero. There's no potential difference. Now, there are situations where birds do get electrocuted by power transmission lines. So the bird can get electrocuted. And the reason is because the other wire, so there's that second wire back there. That second wire, let's say it was a neutral. Let's say it had there is no potential on that other wire. But what if the bird then removed one of their feet and connected it to the other wire? Well, now there'd be a potential difference of 100,000 volts and the bird would get electrocuted. And you'll see that happen with birds that have really large wingspans. Like their wings will like touch one wire and then touch another wire. And as long as there's a different potential, then you're going to get the current flow and then you'll get electrocuted. So as long as you're just touching the same cable, there's nothing wrong with that. Like you won't even notice it. No charge will flow because there's no potential difference. It'd be like if you took like a hot object and touched another hot object, no heat would flow. You need to have that difference in potential. You have to have one that's hot and one that's cold. That's why a lot of times like you'll hear people call these like the hot wire. Like you'll hear people say, "Oh, this is the hot wire." So that way if you touch a hot wire and you touch a neutral wire, that's a difference and that's going to be electrocution potential. So let's talk about in household devices. So these two prongs here. These are the ones that have the voltage across them. So that's where you have the 120 volts across those two. One of those is the live wire or the hot wire, and the other one is the neutral wire. But then this wire here, this wire is called the ground. So I just briefly wanted to talk about grounds because they may save your life. It's a safety mechanism that we use to prevent people from getting electrocuted. So first of all, let's talk about what the ground is. So the way the ground works is there's two ways of grounding. So you can either ground your house by using water pipes. So here's the pipe under the ground. And so that water pipe, you generally want like about 10 feet of this pipe to like go into the ground. And then what you do is you just have your wiring in your house. So here's the electrical box, and you can see that this cord right here is connected to the box. So now you've connected your box through the ground. You've connected it to this pipe that has gone down into the ground. And so the idea is that if you have any like electrical devices in your house that have a loose wire in them, or like a wire gets disconnected, then instead of the electricity flowing into you and electrocuting you, the electricity will flow down into the ground and like discharge safely into the ground without electrocuting you. A second way that you can ground a house is by using these things called the ground rod, which is like a stake that you like pound into the ground, and then you connect a wire from your electrical circuit to the ground rod. So this is what I was telling before. Like, let's say like you have a toaster and there's a wire in your toaster. Like a wire gets loose in your toaster. So instead of the wire like connecting out to the circuit like it normally would, you got like your hot wire and your neutral wire. What if one of those wires got loose? So let's say that the wire like snapped or something or broke off and it actually ended up connecting to the toaster itself. So instead of actually going out like that, the wire got disconnected and loose. And now like your live is like, what am I trying to say? Your toaster is becoming electrified. It's like the metal casing on your toaster is now charged, and there's the voltage on that toaster now. And so if you came and like you went up to here and like went to use the toaster and touched it, then if your feet were on the ground, then the current would travel through you and electrocute you. So what the ground wire does is there's a third wire in here through the wire, like the wire that you plug in, is there's a third wire called the ground. And so instead of going into you when you touch it, if the casing becomes charged, it'll travel through the ground and then discharge safely into the ground without electrocuting you. And so these are grounding wires. They're really important and for saving people in your houses. That's why you always want to make sure that you never remove this thing, because if you remove it, there's a potential that you can get electrocuted if there's a malfunction in the device. Because I've seen a lot of people like in their houses, they have like old style electrical outlets where they only have the two plugs. They're missing that hole, like they don't have the hole. And I've seen people, like I know I've had some friends who will like rip off the ground prong. They'll just rip it off and then plug in their device. I'm like, you should not do that. That's a really bad idea. What you should do instead is just swap out the plate for a plate that has a ground. Just swap it out. It's not too hard to do. All right, let's see. I don't think I want to do this. I don't have time. I was just going to do a quick question where I was going to check to see what would be the current if you touched a 12-volt battery. But that's just going to be plugging in those numbers. You'd put 12 divided by 100,000. You get a really small number. I'm just going to move on because in the interest of time. I didn't even start my timer. What? How long have I been
Yeah,
going? I don't even know.
you've got like close to 10 minutes left. Like
Okay.
you've got until 11:34 to hit 30.
Okay. Sounds good. Thank you, Mayor. All right. So the next thing I want to talk about is that there's two types of current that you'll see in electrical devices, like either in your house or like in your laptop for your phone. What? So there's two types of current. The first is direct current, which is where the current only flows in one direction. So the current just flows from one side to the other side. And an alternating current is where the current can go either direction and it actually actively swaps back and forth. So if you're going to make a graph of the current against time, direct current would just go straight across, whereas alternating current alternates over time. So in one case, you're going in the positive direction and then you're going in the negative direction. So you can see in this picture here, so like at one, that's what that wave there is representing an alternating current. So at one moment, it's going in the positive direction, and then another moment, it's going in the negative direction. So the current can just swap which way it flows. All right, so there's a lot of reasons why this happens. The number one reason though is because it's
Well,
it's much easier to change the voltage for alternating current than it is for direct current. And so power lines like to have less loss when they're operating at a higher voltage. And so that's why we generally transmit power with alternating current, because it's much easier to ramp up and step down the voltage. The other reason is because just the way that you create your voltage
um,
sources. So batteries, yeah, I'm gonna have to mute you since you're making sounds. Let's see.
I was asking a question.
Oh, you were?
Yeah, I was
Now I'm
trying to ask
really
a
embarrassed.
question.
Sounded like you're talking to somebody in the background. Okay, ask a question.
No, I was trying to get your attention, but I didn't want to interrupt.
Just say
So would that
Keppel.
mean that like
Yeah,
I'll just scream next time.
that
So
sounds
would
good.
that mean that like DC is only used for batteries?
Yeah, DC is used with batteries. It's pretty exclusively just batteries. But I'm going to talk to you about a way that you can change AC into DC.
Okay.
So, right. So what you just said, Mira, is exactly right. So like batteries create direct current. And the reason is because the terminals in the battery, like the positive and the negative terminals, they never change. Like that positive side is always positive and that negative side is always negative because there's that chemical reaction taking place that's separating the charges in that way. So the current will always flow. Like if I connect a wire across these two terminals, the electrons are always going to flow towards the positive side and be repelled by the negative side. Whereas in an alternating current situation, what you have is you have some sort of what they call a dynamo or a generator. So this person's going to basically turn this crank. They're going to rotate the crank, and it's going to spin this coil here inside a magnetic field. So this is a north and a south pole. We'll talk about magnets a little bit, but basically there's a magnetic field here, and there's going to be a coil that's spinning inside that magnetic field. And as the coil spins, the current is going to swap. So at one point it'll be like up and down, and then it'll flow one way, and then you spin it again 90 degrees, and now it's reversed, and so the current will flow the other way. And so by spinning that thing, you're constantly making the current go back and forth and back and forth and back and forth. So this is called a generator. Generators work off something called electromagnetic induction, which is what we're going to learn about in a future lesson. But I just wanted to show you how you can create the different types of current. This is what's happening inside every power station. You have a magnet and a turbine, and the turbine is spinning with steam like in a heat engine. Like the turbine is going to spin, and it's going to rotate a conductor inside a magnetic field, and then it's going to create a current. And so because of those rotations, you have this natural like swapping of the direction of the current. So my question is it possible to convert AC into DC? So when power comes out of the power plant, it's in AC. That's because the generator right there is spinning, like I just said, and it's rotating, and it's creating that alternating current where the current's going like that. So if we take the current and send that to our power outlet, and then you want to plug in a device like a laptop, well, your laptop only works off of DC because it has batteries in it. So your laptop is designed to work with direct current. So what you need this device. It's called an adapter. And that adapter is going to take the AC from the wall and turn it into DC so that your laptop can run. So it's called an AC adapter. So you have to, or a DC adapter. Like you have to plug it into the wall. So you're taking your AC alternating current in the wall and turning it into direct current that your device can use. So how do you do this? Well, the trick is you have to make something that's like a wave, whoop, like that's the alternating current, and you need to make it become sort of flat. And so the first thing you do is you use a device called a diode. So that's what this thing over here is. It's called a diode. That's what these guys are. So the way a diode works is it's a semiconductor that only allows current to flow in one direction. So by putting one of these in your circuit, you're immediately chopping off any current that tries to flow the opposite direction. And then that's giving you these bumps. Okay, so we're kind of direct now. Like we only have current going in one direction because the diode has restricted all the other flow. And then the second thing you do is you just sort of store up this charge, and instead of it dropping really quickly, you store it up in a capacitor and let it sort of discharge slowly. And then that's what you're seeing over here is by putting a capacitor next to the diode, the charge that flows through the
Apple, you're being
diode.
really laggy.
Yeah, let me check my connection real quick. My connection looks good. So the idea is that the capacitor is going to store up this charge and then slowly release it. And so you can imagine that the capacitor is kind of like this pool of water down here. And then the water is like the charge. And so here you have your current leaving off through your circuit, and then the water is just storing up the reservoir, the capacitor is just storing up a bunch of charge. So even though your diode, your alternating current is only putting in charge once, and then it has to wait, and then it puts in charge again, and then it has to wait, and then it puts in charge again. So even though you're only intermittently putting charge into the circuit, the capacitor stores up the charge and then steadily releases it. And so that's what allows the current to be more like direct, like sustained like that. Obviously, this isn't good enough because you can still see there's some alterations in there, so it's not perfect. Like you have variable current, you don't want that, so you actually end up using what's called a diode bridge. So that's what's going on here. This is a complicated picture. Usually, instead of looking at like these complicated pieces of how all these electronic devices come together, we create what are called schematics. So that right there is called a diode bridge. This is a transformer, which is going to up or decrease. In this case, it's a step down. So it's taking 230 volts and dropping down to 13 volts. But this thing over here is called a diode bridge. And basically what this does is you have a whole circuit of diodes. So when the current is flowing this way, it can't go through this diode, but it can go through this one, and it goes off to your circuit. Or if the current is flowing the other way when it alternates, you can see that it can't flow through this diode, bloop, but it can flow through this one. And so now what's happening is either direction the current flows, it can go through the bridge. It can go through that diode bridge. And so then that takes us to only having a hump for every time it's going in the positive direction, to then also getting a hump when it was trying to go in the negative direction. And so now you still have your capacitance. You can see it's even more smoothed out now than it was before. It looks like I'm out of time. I have one last thing to talk about. I'll if we don't get to it, that's fine. But like if you aren't able to get to this, if you need to shut off the video for time restrictions, that's fine. But I'm going to keep going. This should only take me about 5 minutes. All right, the last thing I just want to talk about was uh, if you've ever turned on the light switch, you'll notice that the light turns on like immediately. You don't have to wait for the electrons to like flow to the light bulb. Like you just flip the switch and boom, it turns on instantly. And so I just wanted to talk about that. So the first thing to know is that when you put a conductor across a potential difference, an electric field is established inside the conductor. So you can see here that there's this electric field just like everywhere. But then if we put a conductor here, like this is some sort of wire, now you can see the electric field will actually follow the shape of the wire. And so now realize that there's free electrons inside the wire because it's a conductor. And now those free electrons are in an electric field. So as soon as that electric field is established, boom, those charges will start to move. And so it's sort of like a misconception. Like it's not like an electron is hanging out over here and it's like moving through the circuit. That's not what electricity is. What electricity is you immediately establish the potential difference and then boom, this electric field is everywhere in the conductor, and then every single one of these charges, they all, I guess I'm having them go the wrong direction because they're electrons. Electrons go opposite to the field. And then every single one of these electrons will start to flow because every single one of these electrons has a force in it from the electric field that was established by the potential difference. And so the thing is that when I flip this switch, so boop, I'm going to flip down this switch, the light bulb turns on instantly. So we get light right away. And the reason is because there's a wire here and there's free electrons inside that wire. And so as soon as I go boom and flip the switch, the electric field gets immediately established all throughout the wire. There's an electric field immediately established. That gets established at the speed of light. It goes jump through the circuit really quickly. And then every single charge that's inside these conductors, every single one of those charges immediately starts to flow. And so it's not like we had to wait for an electron over here to go through the whole circuit. We didn't have to wait for that electron to make it through the circuit. The electrons that are in the light bulb itself immediately start to move because you've established an electric field. So the thing is like, you also have to remember though that the electrons aren't really able to go too fast because as soon as they start to go through fast, we showed this picture last time. As soon as the electron is going fast, it's going to bonk into one of those lattice atoms or one of the atoms in the conductor. And it's going to immediately go bump and it's going to lose its energy and that energy is going to get dissipated as heat. So what we have to imagine is like what's really happening here is like as soon as the electron starts to get accelerated by the electric field, it's going to suffer a collision with an atom and then bounce off of it. And then the electric field's going to be like, hey, get back here and then pull it back again. So the electrons actually, as it travels through, so the electric field is pointing to the left, so this electron's traveling to the right. As the electron actually travels through the material, it's actually going to take this really random path through the conductor. And that is going to cause the electrons to have a drastically reduced average velocity. So not only can they not go fast because of the collisions, they're also going to slow down due to these collisions and get in these weird directed, different, crazy random paths. So the overall rate that the electrons flow through a conductor is called the drift velocity. And electrons go super, super slow. So I'm just going to show you guys this question real quick. This is a picture of my streaming setup. I'm sitting in that chair right now. So what you'll see is that I've got alternating current here from the wall. So that's an alternating current. And then this is my adapter right there. That's the thing that has those diodes and capacitors in it that allow it to, well, it does two things. It drops down the voltage from the 120 volts in the wall down to like, a couple volts, whatever my laptop needs. So, and then the other thing it does is it switches the alternating current into direct current. So this is it's an AC adapter, so like, or a DC adapter. So it gives me DC from the AC. So my question is, after I plug in the cord, about how long will it take an electron from here to travel all the way up this wire and into my computer? About how long would that take? And the answer is quite shocking. So if you just want to wait for one electron to flow through this direct current. Now remember, you can't wait for an electron over here because it will be moving both directions. So as soon as it moves this way, the current's going to swap and it's going to go back to here and it's going to go back to here and it's going to go back to here. So those electrons never move because it's an alternating current. But once the alternating current gets switched to direct current, that electron is going to flow through that wire. And then it's going to flow back again because there's actually two wires here and it's going to go back to remember how there's two prongs here. So there's actually a double wire, which is something that people don't realize. Like you look at this wire and you're like, oh, it looks like one wire, but it's actually two wires, one going one direction and then one coming back again because you need the voltage difference. So you have to have the two wires. Anyway, the time it takes for the electron to travel from the adapter to my computer is about 5 hours. Electrons travel really, 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 really slowly. How long does it take for an electric current to be established in the charging cable? So after I plug it in, how long does it take from when I plug it in to there being a current flowing through this cable? And the answer is it's nearly instant. And that's because the electric field slash current, let's write both, the electric field and the current are established at the speed of light. And the speed of light is 300 million meters per second. So electric current, electric field, electric current are established at the speed of light. Electrons move slow, but electric currents get established quickly. That's the main idea. All right, I'm done. Mayor, if you have any questions, I'll just take it after I stop the video. But I'll see you guys later. Have a wonderful day.